This presentation on spectrophotometric quantitation of nucleic acids has been prepared for the University of Alberta and is presented by Dr. Karen Matika. Copyrighted material contained herein is reproduced under subsection 29 through 29.4 of the Canadian Copyright Act. This document or presentation is available for your individual use. Further distribution may infringe copyright. By the end of this presentation, the learner should be able to calculate the concentration of nucleic acid in a solution using absorbance. The learner should also be able to determine the purity of a nucleic acid solution using absorbance ratios and identify probable contaminants. We'll start with just a brief background into absorbance readings. When a polychromatic light hits a colored solution, some wavelengths of the light are absorbed while other complementary wavelengths are transmitted. The transmitted light is the light that we see with our eye when we look at a colored solution. Transmittance is commonly expressed as a percentage. The percent transmitted light is equal to the amount of light seen by our eye compared to the incident light, times 100%. As the concentration of a solute in a solution increases, the percent transmittance decreases and the absorbance increases. The relationship between absorbance, A, and transmittance, percent T, is logarithmic. Absorbance equals 2 minus the log percent T. The absorbance of a colored solution can be used to determine the concentration of a solution. The relationship between the concentration and absorbance follows a modification of the Beer-Lambert equation, where the concentration equals the absorbance times the molar absorptivity of the solute divided by the path length of the spectrophotometer, or the cuvette size. The concentration of nucleic acids in an aqueous solution can be quantitated using the absorbance of the solution. Instead of using the Beer-Lambert equation, typically the absorbance of an unknown solution is compared to the known concentration of a nucleic acid solution at the absorbance of 1.000 at 260 nanometers. The concentration of a pure DNA solution with an absorbance at 260 nanometers of 1.000 is 50 micrograms per milliliter, and the concentration of a pure RNA solution with an absorbance at 260 nanometers of 1.000 is 40 micrograms per milliliter. To determine the concentration of an unknown pure solution of DNA with an absorbance at 260 nanometers of 0.750, it is compared to the known concentration for a pure solution of DNA with an absorbance of 1.000. The equation can be rearranged to solve for x, the concentration of the unknown. X equals 50 micrograms per milliliter multiplied by the absorbance of the unknown, 0.750, divided by the absorbance of the known solution, which is 1.000. The concentration of the unknown solution with an absorbance of 0.750 is 37.5 micrograms per milliliter. Take the time now to stop the video and try these 3 practice questions. The first question asks you to determine the concentration of an RNA solution. This is very similar to the example on the previous slide, except this question is talking about RNA and I threw in a dilution. To determine the concentration of the RNA, you multiply the known concentration of RNA at an absorbance of 1.000 by the absorbance of the unknown and by the dilution factor. So we multiply 40 micrograms per milliliter by 0.750 and by 50, the dilution factor. The concentration of the RNA solution is 1500 micrograms per milliliter. The second question asks you to calculate the total amount of RNA in 500 microliters. To do this, you multiply the concentration of the RNA solution by the volume, 500 microliters. The total amount of RNA in 500 microliters is 750 micrograms. The third question asks you what volume of RNA is required for 750 nanograms. To determine the volume, you will need to convert the concentration from micrograms per milliliter to nanograms per microgram liter. As you can see from the equation, 1500 micrograms per milliliter equals 1500 nanograms per microliter. To determine the volume, divide the required amount of RNA, 750 nanograms, by the concentration, 1500 nanograms per microliter. The required volume of RNA is 0.5 microliters. In the lab, DNA and RNA can be isolated from a variety of different sources such as blood, urine, tissue, and bacteria. Most commercial kits yield pure DNA and RNA. However, it is still good practice to check that your nucleic acid preparations are free from contaminants. This is done by measuring the absorbance of the aqueous nucleic acid solutions at 3 wavelengths, 260, 230, and 280 nanometers. The ratio of the absorbance reading at different wavelengths is used to determine purity. A 260 to 280 ratio of approximately 1.8 is generally accepted as being pure for DNA. A 260 to 280 ratio of approximately 2.0 is generally accepted as pure RNA. A 260 to 230 ratio of 2.0 to 2.2 is generally accepted as pure for both DNA and RNA. For DNA, a 260 to 280 ratio of approximately 1.8 is generally accepted as pure, whereas for RNA, a ratio of approximately 2.0 is accepted as pure. A low 260 to 280 ratio can be caused by the presence of nucleic acid extraction reagents such as phenol, or by the presence of proteins. An increased 260 to 280 ratio is not associated with contamination, but could indicate a problem with your spectrophotometer. A 260 to 230 ratio of 2.0 to 2.2 is generally accepted as pure for both RNA and DNA. EDTA, carbohydrates, guanydium hydrochloride, and phenol all absorb light at 230 nanometers, and if present in a nucleic acid solution, can produce low 260 to 230 ratios. 260 to 230 ratios greater than 2.2 are not associated with contamination, but instead are associated with procedural errors such as using a dirty pedestal for measurement or using an inappropriate blanking solution. At 260 nanometers, a pure solution of DNA with a concentration of 50 micrograms per milliliter has an absorbance of 1.000. At 260 nanometers, a pure solution of RNA with a concentration of 40 micrograms per milliliter has an absorbance of 1.000. A 260 to 280 ratio of approximately 1.8 is generally accepted as being pure for DNA, whereas a 260 to 280 ratio of approximately 2.0 is generally accepted as pure for RNA. A 260 to 230 ratio of 2.0 to approximately 2.2 is generally accepted as being pure for both RNA and DNA. The following reference was used in the preparation of this video.